at the University awarded in 2015. And then afterwards, he moved to the Netherlands at JIVE as a postdoc, and since 2019, he's staff member at JIVE. So he's an expert in VLBI. He started from high energy transients. He's an expert in transients, several classes. And today he will talk about a specific class, which is a new class of burst radio burst. And I will leave you.
Okay, thank you very much. So thanks everyone for coming, and thanks to Cristiana for inviting me. It's always a pleasure to come back to Bologna. I'm really happy to spend these 2 days here. As I said, yeah, I'm Marcote. I'm mainly an observational astronomer. I come from high energies, but I've always been studying all the systems through radio observations. So I'm in the high energy world, but always from a radio astronomer. And actually that led to quite a variety of science during the last years. And especially in the last 3-4 years, I got almost my time involved on fast radio bursts that some of you might have heard, some others is quite a new topic. It's not a really old field in particular. So in this colloquium, I will try to do a review on the topic, like what are fast radio bursts, what we know from these sources, what we've learned in the last years, and the strategy that we followed in our group, which was to observe them at very high resolution to try to understand which objects can produce this burst and where are they localized, where they are actually coming from. And maybe some of you have saw me 2 days ago because I was doing the colloquium in Marcote. This is completely different topic, so it won't be exactly the same talk. Don't worry about that. So this is especially the topic that I skipped in that talk, which is just the fast radio burst. I will go in detail on this one here. And yeah, I'm working at JIVE in the Netherlands, which actually we are doing our 30th anniversary. So we are happy for that there. And as I said, in this talk, I'm going exclusively to talk about fast radio bursts. The first part of the talk, it will be only about trying to explain you and make it easy to understand what we call a fast radio burst. And I will just do a quick summary of what we know so far about them. Then I will move to our strategy, which was the very high resolution observations with VLBI, very long baseline interferometry, because this is the only way to pinpoint where in the host galaxies actually these bursts were coming from. And I will just move with the results that we've been getting in the last 5 years and how actually our knowledge of these sources has been dramatically changing almost every year, because still it's a really new field. All our ideas and preconceptions are still like on the way changing. We think that we are trying to understand a bit better every time what are these bursts, but still we're on the way that many ideas can change quite quickly in time. So I will give you here the current summary on the topic. So starting with the basics, what is a fast radio burst? Well, the name is quite descriptive with the 3 words actually, and we call them fast because this is an isolated signal that only lasts 1 millisecond. And when I say that lasts 1 millisecond, I'm talking about the total emission of the event. Like if we think, for example, on GRBs, we can talk about 1 second, second duration burst, but then later we have a kilonova, we may have an afterglow. There is emission on later stages that last longer. On fast radio bursts, there is only this emission on 1 millisecond, and there is nothing else related to these events. There is no emission before, there is no emission after related to this burst. So the only thing that we have is a burst that lasts of the order of 1 millisecond. And the radio is because so far we've only observed them at radio frequencies. In particular, between most of them, the 0.4 to gigahertz. So we've been always subscribed to the radio domain, but actually, as you will see later, not only radio astronomers are interested in fast radio bursts because they have different implications. We still don't know if they are emission outside the radio domain. We think that at least in several of them we should detect emission at different energies. But so far, this is the idea. Almost all fast reverse have been detected only at in the radio domain. And they are particularly bright. They can be easily detectable with any small radio antenna. So you don't need a big observatory to detect them. I will put as a sample in the last 2 weeks, there was one fast reverse that was particularly active and bright. And actually, even with the telescope that we have next to our institute in Dwingelo, the Dwingelo telescope that has 25 meters, is not a professional telescope anymore since the 80s. It's run by amateurs. Actually, they catch a few bursts from this particular FRB with the current system there. So they are really bright. And I mentioned before briefly that the field is really young. And when I say young, it's kind of one of the youngest that we may have in astrophysics. The first reverse was only detected in 2007. And this was not something that actually we expected. Like, it's not a field that you expected to be there, but you didn't have the instrumentation to detect. This was kind of surprising events. And even if the first one was detected in 2007, there was not until a second one was kind of detected in 2013, when the community believed that this was truly astrophysical signals. So we are talking that basically the field is around 10 years old only. And that's why it's still evolving dramatically on short time scales. Since then, we already know thousands of fast reverse, mainly almost all of them discovered by the same instrument that I will detail later, which actually can introduce some bias on the population that we have. But in general, we have quite a big population of fast reverse already, on the order of thousands. From those ones, actually, we know that only a very small fraction, 5% of all these 1,000 events, coming from sources that produce more than one FRB. So on the vast majority of the population, we only see one burst and that's it. There is no other emission coming from the same area in the sky, from the same source. Only 5% of them exhibit multiple bursts. And in any case, this is not like a pulsar that you have a period where you see the burst. They are completely random in time. But we know that a few sources may exhibit different bursts with different arrival times, like they are not predictable when you may observe bursts. And the interesting part, of course, but then the bottom neck is that we still don't have a fully strong picture that can explain the emission that we observe. We are narrowed down the possible models, but there are many ifs and many open questions there that we cannot explain fully. The only thing that we know is that fast reverse are an emission that comes from a very far distances, like they're extragalactic, and in general, they come from quite high redshifts. And this is because even if the emission is so short, what we observe, because from that distance is this, like this is a real snapshot of one FRB. The axes are time and frequency. So what you see is a really narrow emission on the order of milliseconds, but actually it's completely dispersed. So at different frequencies, you observe dependency on the square of the frequency that goes. So at lower frequencies, you see the arrival time to be later. And this is just because the signal propagates in non-vacuum, not completely vacuum medium. So then the signal gets dispersed. The good part from there is that this tail is actually just proportional to the amount of electron content that the light crosses through. So with this, we can have an idea about how much material is between the source, the emitter, and us, the observer. And the key point here is that if we take into account all the material that is in our galaxy in the Milky Way in that particular direction, and this applies to actually all FRBs, the dispersion that we would expect, it was much lower. So the signal should have been dispersed in much narrower time scales than what we observed. So that implies that there is way more material that the light crosses than the one that we know from our galaxy. So the only way, easy way to explain that is that these systems are extragalactic, and then you need to take into account all the intergalactic medium there. And from there, you can actually derive an estimation of the distance to the source. It's not perfectly accurate, of course, because it depends on the lines of sight, but you can get a good enough estimation of the distances. And because of that, we know that most of the FRBs here, I'm talking on the population level, come from redshift between 0.1 and 1. Of course, this has details, so there are a few FRBs nearby and other ones farther. But then this is the bulk of the FRBs that so far we've been discovered. And the problem that at the time encountered with this is the luminosities. So these signals, if you see in the flux in your data, it looks exactly the same as a pulsar, but without the periodicity. So it's the same time scales, kind of the same fluxes, same shape. But then we place that not in our galaxy, but quite far away. So that means that the luminosity, the intrinsic luminosity is way higher than the one from pulsars. And that has been traditionally the problem to explain fast radio bursts. So in this plot, we have basically the time duration in the x-axis of the emission plus the luminosity on the y-axis. And if we know the pulsars are always in that area here, like all the pulsars that we know. So they have roughly similar luminosities within the orders of magnitude. But then if we consider distances of fast reverse, those are placed here. Same time scales on the order of milliseconds. But if you see the y-axis, these are roughly 10 orders of magnitude gap in luminosity. And that was the problem, like you cannot just escalate the emission mechanisms from pulsars 10 orders of magnitude to explain this emission. And that has been traditionally the problem there. Yeah. The other one, it was the rate. So I mentioned that so far we discovered thousands of them. And based on our current sensitivities, our current sky coverage with the instrumentations, we predict that actually the rates of fast reverse are really high. So in terms of the current sensitivity of radio instruments, we know that we can detect of the order of, or we could detect of the order of 10 to 3, 10 to 4 fast reverse per sky and per day. Of course, we don't discover those days because we are not covering the whole sky per day. But actually, taking into account the luminosities, that translates to rates of 10 to 5 fast reverse per cubic gigaparsec and per year. And these rates are actually much higher than the ones that we know from known transients like supernovae, GRBs, or so on. That's why we couldn't relate those ones to other kind of sources that we know that are out there, because there was no way to escalate to these rates there. So this was the problem that we had in the field in the last 10 years. Of course, in between, there were so many different models. So they tried to predict FRB emission from completely different scenarios. And the problem until 3 years ago is that for the vast majority of the times, we had way more models than actually FRBs. So it was almost impossible to narrow down which models were could be right or not. Also because the data that we had was quite sparse. We only had the burst. So we had an estimation of redshifts and the frequency that was observed, but little more. So there were not that much data to narrow down a system. So this is what applies to almost the entire population of fast reverse. I will just now highlight one in particular. That was the only case where we observe a FRB light emission. It's similar to an FRB. The luminosities were quite lower, but it's the only time that we see similar emission in our galaxy. And that actually came from a known galactic magnetar, which is actually a known gamma ray repeater, soft So gamma, sorry, suddenly it's went off my mind. So this was a known one. So we got the burst that you see in the left that resembles the same as a fast river emission. The only thing is that the luminosities are much lower, a few orders of magnitude lower than the normal FRB, so that's why we call it FRB-like emission. But on the other hand, it was similar in all other aspects. So this happened in 2020, actually during one single observation, and actually it emitted again in 2022. That most of the data are still under analysis on different teams there, but we observed that actually this happened again. So the signal was quite bright, on the order of kilojanskis, megajansky per millisecond, so it's much brighter than the normal burst that you may see in these sources. And the most interesting part is that there was a simultaneous X-ray burst in this one. So during the FRB emission, it was during those moments that you had X-ray bursting emission. And actually, you can see that better here. The gray light curve is the X-ray. So you saw the 3 bursts that they were emitted there. And in 2 of them, there was radio emission, which is the orange curves there. So the 2 FRBs, observed and radio domain, they were linked to X-ray bursts. And there was a third X-ray emission that didn't have a companion in the radio domain. In any case, the radio emission actually was just a bit ahead on time compared to the X-rays. And this was really important because this was the first time that we could narrow down, or at least we boosted all the theories, that there were most of them, that link that FRB emission may come from magnetar-like objects with some extra context or different environments, different conditions. But we knew that likely the objects that needs to be there fully emitting the fast river emission, it's likely to be magnetars. And a part of that, the idea that we had X-ray emissions coming with radio, and because of the delay, we could actually narrow down that this is actually likely to happen within the magnetosphere of the magnetar, like really close to the surface of the magnetar, as opposed to different models that are still not completely ruled out that predict that emission may happen farther from the cylinder, light cylinder, just by interactions with the surrounding medium of the shocks that happen there if we are in young magnetars. In any case, this has been the only case. For all the extragalactic one, we cannot completely verify that there is a magnetar related to it. So with that, we go to the general ideas on this field, which is why we should be caring about fast reverse. Well, first, as astronomer, of course, because you have a mission that is really bright, you cannot fully understand, so it's always interesting to try to understand their new events, especially from the transient community. You always look for new things. But the important points also from outside the radio domain, radio astronomy, is that FRBs can have quite important implications on the population level on other fields. So the fact that we have a signal that is so narrow in time, just 1 millisecond, and comes from such a long distance, means that actually that light carries on a lot of information on the medium that it crosses through. And because of that, actually, there has been already some studies with the current populations that can trace quite particular and narrow properties on the galactic medium, especially halos, for those FRBs that actually crossed a galaxy halo on the way to the Earth, and also put a lot of constraints on the history of the universe in terms of hydrogen ionization and in fundamental physics, because you can put tight constraints, especially for the farther FRBs, on the equivalent principle on photon mass, because you have different frequencies and you see how actually that light traveled quite in detail. And actually, there were already some preliminary constraints on the baryon content of the universe that actually was the best constraints or points to be the best constraints just based on the population of fast reverse. So that's why there are a number of fields that actually are interested on having a well understood population on FRBs with good distant measurements and then the properties on them. The problem, even if you have thousands of these sources, is that for most of them, they are poorly localized. And when I say poorly, I mean on the order of tens of our minutes. And this applies for almost all of them. And the problem is that as you don't have any other emission after the burst, as with GRBs, you cannot actually link them to any associated counterparts because you don't have anything in the area that changes and then you can correlate it to the actual FRB. So that's a problem that you have with most of them. You have only estimation of the redshift that, of course, puts some constraints on the sources that you may see in the field, but still you have hundreds of possible counterparts that you cannot distinguish. And this is the problem that we realize and we know so far. So this was the first idea that we had, that we really need to localize FRBs at a much better level. So getting much better localization of these FRBs. So in that case, we can actually understand at least the host galaxy. And if we do better, do even to understand and unveil the local environments. And the thing that most of them are that poorly localized is that almost the entire population on FRBs have been discovered by the CHIME telescope in Canada. That is really good discovery in FRBs, but of course it has a poor localization on the order of several minutes. So it's really good to discover and actually increase the population on FRBs. And again, this one is the one that has discovered thousands of them, and is the one that unveiled that tens of them are the ones that saw multiple bursts. And in any case, this is not a steerable observatory. It actually skies the sky all the time. So it's really good to understand the activity of these FRBs that actually saw multiple bursts. And we know that some of them actually just may exhibit many of bursts clustered in a very, really brief period of time, like 1 month or a few weeks. But then it may be years when you don't see any bursts again. And then, yeah.
Yes, how do you know that it is a repeater and not different?
Yeah, okay, that's a question. You know, basically because of the light, like a. Okay. Yeah, because of the dispersion, you can have you have a measurement on the dispersion measure, which is connected with the distance, or at least the content that it passed through. So you see, yes, you see that dm is the same for different bursts within the same per minute scale in the sky. So that's why in some cases you may rule and then you may have some chances, and that's why actually the data takes a few years in some cases to really demonstrate that they're the same. But then you see that the dispersion is really constrained to a particular FRB. And if you see the same one from the same area, you can be pretty sure that it's the same FRB. I mean, the same object producing the different bursts.
We have also a question from
Fernand.
So is there a full catalog?
Yes, there is.
Yes, there is.
Already answered.
We can find. And there is even another one, I think, or 2 or 3 for itself. Yeah. We can put after. Yeah. Of course, this is not the only observatory detecting or trying to discover FRBs. There are different ones. Basically, in the last years, we got quite a number of FRBs discovered by the DSA in United States, that is an expanding array, or ASCAP or Marcote, that are detecting, but then the rates are way lower. They detect tens of FRBs. So it still is a large number, but compared to the CHIME one that is thousands, still is a minority of them. And that's why I'm thinking that we need always to take into account that our current population is observational bias, in the sense that this is an instrument observing in a particular frequency range, 400 to 800 megahertz, and it's the one detecting FRBs. So our population is biased to those ones that emit significantly in those frequency ranges, plus the stuff that can come from there. So the thing that we were wondering during that time, and this is how our actual studies started, is that to really understand what objects can produce FRBs, we really need to understand which are the possible progenitors where the FRBs are produced, like what are in these regions in the sky, which objects can be linked to the FRB production. And we really need to understand what are the objects that can produce FRBs, where we can localize them. And to that, we really need to have really accurate localization of FRBs, so we can at least explore what is in this area, where are the objects that may be in that area, and what are the local environment properties where the FRBs are produced. And maybe with that, we can narrow down the models. But for that, again, you need better localization, so higher resolution than those current instruments. So what we did in our group is to observe with the European VLBI Network, that is a global network of radio antennas, including the 3 antennas from Italy. And in these ones, we observe with all of them together, we combine the data. So with that, we have an equivalent antenna of the order of the Earth in diameter. So in that case, we are talking about resolution of the order of milliarcsecond. So with that, we knew that we really narrowed down where the FRBs are known, because even at the beginning that we didn't know that we're extragalactic, we were thinking that if it's in our galaxy, in any case, we are tracing positions that imply distances of the order of astronomical unit. And if they are extragalactic, in any case, we are talking about sizes of the order of parsecs. So we can really pinpoint in a putative host galaxy where within the galaxy the FRBs were produced. And actually from the observatory at JIVE Institute in the Netherlands is when we combine coordinate observations and we combine the data. So this is what we started already several years ago. And actually, together with the VLA, is how we localized for the first time a FRB with enough precision. And what we found is the image on the left. This is the optical image. And we found that the FRB was coming from a low metallicity dwarf galaxy. And actually, this dwarf galaxy had a prominent star-forming region, which is the black knot that you see in the image. And the FRBs were coming from really inside this star-forming region. Furthermore, from the radio domain, which is the left image for you, so, we saw that the birds are actually physically linked to a persistent radio source there, which is the one that you see in colors, which is at 5 gigahertz, and the contours is just different frequency, 1.7. So we have lower resolution at that frequency. That's why these contours are larger than the color one. But that's the actual source there. And the crosses just indicate the different birds that we localized. So this source, it was interesting because it's really compact. It's less than 0.7 parsecs in size. We could only constrain an upper limit on the size. But actually, this is quite constrained. It's already lower than the standard supernova remnant pulsar wind nebulae that we know in our galaxy. Because we think if this is related to young magnetars, maybe that's what we were observing. On the other hand, we cannot reject the idea that this may be related to a massive black hole emission still, because it's really compact and it's quite constant and persistent in time. In any case, the birds are linked to this source, and this is so far. Later, we found this last year another second one, but those are the only 2 FRBs that are linked to persistent radio continuum sources. So for all the other ones that have been precisely localized, we don't see any continuum emission related to the birds. So at the end, this one ended up to be quite a special case, but at the beginning, being the only one that we knew, we didn't know that part, of course. So the first thing that we started thinking is that this is a low metallicity dwarf galaxy with a prominent star-forming region. And we know that there are other sources, or the transient sources, that are actually found in these conditions, which are the long GRBs. This is the best places where we find most of the long GRBs. So that's why at the beginning we thought that maybe there is something there, although later on with the following localizations, we actually weaken this approach there. In any case, this was the first one. And as I said, we still cannot rule out completely what is the object there that produces the FRBs. We think that there must be a magnetar, a really young magnetar there, because of energetic and activity constraints. We think that this is a really young one. Most of the models predict years of 10 to 100 years old, no more. So we are talking a really, even on lifetimes, young scales. But again, the persistent radio emission can still be explained by both models, like a superluminous supernovae, because the luminosity is still really bright, but it's really compact in size, so it needs to be also really young. Or we may have a magnetar interacting with a massive black hole, that in that case, you can explain why this is so compact. Still, of course, we don't rule out other models that are there, but the first two are the most plausible ones in terms of, compared to other FRBs there. But as I said, this was the first FRB that we localized. When we found a second one, when we localized a second one, we found a completely quite different environment. So the second one that you can see on the right bottom image was found in a spiral galaxy, Milky Way like size. So actually this rule out that FRBs may be found on dwarf galaxies only. The interesting point is that this one was also associated with a star-forming region. That is what you found here. So that dark blobs, it's the HST images, and this is star-forming regions in that area. And the yellow point is where we found the FRB. And thanks that we have such a high resolution with the EVN, we can actually, the HT images, we can actually pinpoint them compared to the galaxy. And we actually saw that the FRB is not, as in the first case, inside the star-forming region, but it's actually outside the edge of the star-forming region. So if you consider the typical lifetimes of magnetars, there is no way that you can have a magnetar form in the star-forming region, which is where you expect it, and travel because of the kick after the supernova to such a position, and the magnetar still be active. So in these cases, most of the, in this case, the only way to try to explain that with a young magnetar is that it's in a binary system. So you have, like in systems that we know in our galaxy, you have a recycling time, the magnetar activity, let's say period, can live much longer. And that's the way that we can explain this localization there. Another point, another information that point us towards this interpretation is this, like this FRB exhibit periods of time where all the bursts are found. And outside these periods, we don't see bursts. And the thing is that these periods repeat within roughly 16 days. So every 16 days, there is a window of 4 days where we can find bursts. They don't guarantee, like it's not completely periodic in time, the bursts, but we know that there are these windows of activity. And 16 days matches quite well the known X-ray binaries that we know in our galaxy. Like we have many of them on that order in orbital periods. So that's why this kind of hypothesis won some track at this time. In any case, we also discovered from this source that the FRB emission roughly is on the order of milliseconds, but you can have components much narrower than that. So in this one, we discovered things that were on components on the order of 1 microsecond. So it can be even much faster than the millisecond classical emission. In any case, the association between FRBs and star-forming regions, at least the ones, the repeating FRBs, the one that produces multiple bursts, was actually going there with a new localization. So this was another one that we also found next to or inside the star-forming region, And it was one particular case that demonstrated why we really need such a high resolution as VLBI. Because on the left, you see the different localization from different instruments. This was quite active. Different observatories found it and localized it. The yellow cross is just the center of the galaxy that occupies the whole field. And all of the localizations were on the order of 1 arcsecond. So actually, you couldn't distinguish where in that galaxy, next to the center of the galaxy, in the outskirts, the FRBs were coming from. But the AVN image is the color one. And then you see that our resolution is basically 1,000 times better. So we can really pinpoint where in the galaxy. And on the right is the continuum image. There is nothing associated to that FRB. But then those contours is a star forming region that is there. So we could narrow down that FRB is actually coming from inside that star forming region. The problem on this track that, okay, we think that FRBs are associated with really young systems, so it makes sense that they are in star forming regions. But then this link kind of dropped, or at least we need to do some exceptions since last year, where we actually discovered this particular FRB that was inside that bright spherical object there that is actually a globular cluster. This was the surprise that we got with this particular FRB. So this is radically the contrary of star forming region or any young region. This is a globular cluster. You don't expect anything really young to be there. And actually the bursts, which is the red blob in the image, they are quite close to the center of the globular cluster, but actually outside the centroid of the globular cluster. So how can you explain to have a young magnetar in a globular cluster? It's impossible to do it through the normal channels of core collapse of a star because you don't expect that type of systems there. Still, the most promising hypothesis is that maybe we still have a young magnetar, but produced by accretion-induced collapse of our galaxy, or like merger of two systems in the global cluster, or is associated with low mass SR binaries, which are commonly found in global clusters. And this is the final localization that we did. I will do just a brief note on how our images look like actually. And this is why we focus on the ones that actually show multiple bursts. If you only have one burst, it means that you are producing an image on 1 millisecond, if you're lucky, of time on VLBI. So that means that the images actually, they look like the one on the top level, and you can only get localizations of the order of hundreds of milliarcseconds, which still is really good because you can really pinpoint in the galaxies. But then it's not as good as we can do with multiple bursts. So the moment that you add multiple ones, we recover basically a localization with a precision on our resolution, so on the order of a few milliarseconds. And this FRB was special not only because it was in a global cluster, but also on the luminosities and narrow components. So this FRB, the bursts from this FRB are the black stars. And you see that actually filled a bit the gap between FRB population, pulsar population. Actually, with luminosity similar to the ones that we saw in the galactic magnetar that I mentioned at the beginning. And furthermore, in this particular case, we discovered some components within the burst that are as narrow as 60 nanoseconds. So actually, we are moving in the diagram from the time scales to the really short, even shorter time scales. And actually, we were at the level of the Crab nanoshots, with a bit higher luminosity, but on that level. And actually, this was even a stronger constraint on where in the putative magnetar this emission can come from. Yeah, okay, that's good. Because if you have such a narrow emission, it cannot come from farther away, just shocks or boosting emission on shocks outside the light cylinder. You really need a really compact, even if it's Doppler boosted, the emission, you really need a really compact region where the emission is produced. So this was the most harder constraints that the emission must come from, so really the magnetosphere of the magnetar. In any case, summary, we had these cases where we demonstrate why we really need such a high resolution, because the details on where within the galaxy, where even respect to possible star forming regions are, they can play a major role to understand the phenomenology or the mechanisms where the FRBs can be, even the nature of those objects. So that's why we continue with this approach. And as I mentioned before, this one, the first FRB localized, it was the only one that is associated with a persistent radio continuum source. None of the other ones. And actually, in the last 2 years, we discovered a second one that is a completely twin of this first repeater. So both of them are associated with persistent radio sources that you see on your left. This is the continuum emission. And both of them are localized in dwarf galaxies with star-forming regions. And the FRB comes from inside this star-forming region in the 2 dwarf galaxies. On the right panel, I just saw what was our localization, our images of the bursts. But again, in this case, we only had one, so that's why we have a bit uncertainty between the different fringes in the map. But in any case, we could demonstrate that it is associated with this persistent source there. This galaxy is a bit farther, so our constraints in the sizes, they are a bit poorer, but still, we know that this source is quite compact, less than 9 parsecs in size. We think we can improve in the future, and the FRB, because of the uncertainties in the image, we can put an upper limit of at least 80 parsecs from the persistent radio source. So in any case, we need that they must be linked. And furthermore, because of the constraints in the size of these persistent radio sources, plus the assumed ages that we can have there, we can actually start ruling out different models. So on the right, you see the constraints and the only possible way for a magnetar wind nebula model. So if we interpret the persistent emission like a pretty powerful magnetar wind nebula, because of the size of the source plus the energy that we see, the energy of the persistent emission plus the burst, we can put constraints on the age plus size of the nebula. And then we are actually going into a really narrow possible parameter area there. The other one is that we have now 2, so we can actually start comparing to sources that we know. So on the left diagram, we have the physical sizes of different objects plus the luminosities. On the bottom part, we have all the known supernova pulsar wind nebula in our galaxy, or extragalactic, some of them. On the higher part, we have the low luminosity AGN. And the blue triangles represent the 2 FRBs with persistent radio emission, with upper limits on the size. So we know that they are at least smaller than that. So those luminosities are much higher than the known pulsar wind nebulae, supernova remnants, but actually matches the ones from all those greenish triangles that are actually, sorry, persistent radio sources found in nearby dwarf galaxies. So these are common radio sources that we find in those galaxies. Still, we don't know if it's supernovae, supernovae, or like the expected massive or intermediate black holes that can host in those dwarf galaxies. But actually, the luminosities matches those ones. And we only have really poor size constraints on most of them. In any case, this is what we've been doing in the last years, and these are the FRBs that we've been localizing. Of course, this implies a lot of observing time, because again, you cannot predict when an FRB will be occurring. And it took a lot of effort, so actually we had 2 projects on that. One is the PRECISE, so we were using these small dishes of the ABN to get more observing time, because it was impossible to fit all our wanted observing time within the regular ABN observations. And this is our under our AstroFlash group. That at the beginning we started with 2 people. Nowadays we have of the order of 20. So actually it increased a lot. And then Still, the data has increased in a much faster way than the people that we have, but we've been there. So in the last years, we've been covering thousands of observing hours thanks to this strategy that started with putting in common the different antennas that are not oversubscribed. So using the green time of all those ones, including the Italian dishes there that observe quite a lot of time actually. And only when we detected that FRB, we had an official proposal in the EVN to correlate that data. And actually in the last 2 years, this moved to the EVN Lite mode that the EVN put available to be able to do this under the EVN frame. So in this time, we discovered a lot of FRBs, but I always want to do this remark. We are detecting many signals, but they only last 1 millisecond. And you don't know when they are observing. So actually you need a lot of observing time to detect these signals. So actually our signal level is of the order of 10 to the -7, meaning that we require thousands of hours to detect a few milliseconds. We got many localizations, but it still is less than 1 second of useful signal. But still, the output was good enough that actually we got these observations. And I will just conclude with a couple of slides. I mentioned here what we've been doing with precise localization, why they help, and actually within these observations, how we could do even at high temporal resolution that actually narrow down the models. But the third thing that we can actually do with all these bears is study the energy distribution of the bears. As I saw here, we have quite a variety nowadays in luminosities, also time scales. But thanks that we are using small dishes and not big ones, we are actually able to catch the brightest bears that in a huge dish actually you cannot detect because it already saturates the signal. And that's actually demonstrating in the last year that this can be really interesting to study the energy distribution of the FRBs. So we see the normal tail exponential cutoff, exponential almost, on the population of FRBs. But actually, when we started getting a lot of observing time and we could actually put useful data on the higher end in energy, we saw that actually there is a second component coming there. So the slope really changes. And these are still only the first studies that we are doing. So now we are entering the phase that we are actually seeing this distribution. But we are seeing this in at least 2 FRBs, and we think that maybe there in other ones. And as I mentioned, some of them have this period of activity that we still don't understand. This was one case where we can have hundreds of hours with no bears, and then within 20 minutes, we detect 40 of them. We still cannot fully explain why this happens, but this has been observed in different ones. And in many of them, we've seen that they are components on the order of microseconds, sorry. Even narrowed down, but then of course, dealing with the data is harder. That's why we haven't done a full study on the nanosecond scale emission, but we think that they are there. And just in this month, we have the particular FRB on the right that is really active. And within a few weeks, we already detected hundreds of them. And if you observe with FAST telescope, the 500-meter telescope in China, they actually have rates of 500 bears per hour. And with that, I will just finish this talk. I hope that you saw that the FRBs are really interested and still have a lot of potential on different fields. We are still trying to narrow down the nature of these objects, or at least the objects that can emit FRBs. We think that there may be a variety of different actual systems that can produce FRB emission. But then, of course, we still need really more precise localizations of them because we are in the level that we have basically one with different properties each. So we cannot do statistical studies on the hosts there. And thanks for attending.